Okay, in this example, que es 3D, we determine divergence and curve. This is the function P, this is the function Q, and this is the function R. The formula to compute divergence is partial derivative P with respect to X plus partial derivative Q with respect to Y plus partial derivative R with respect to Z. Partial derivative P with respect to X is exponential, que es the same. It's e to the X sine Y, because Y is considered like a constant. Partial derivative Q with respect to Y when on exponentially down is a constant, because you differentiate with respect to Y, and derivative cosine is minus sine, so it's minus e X sine Y. And finally, partial derivative R, que is the last function with respect to X is 1. This is cancelled, and the divergence is 1. 1, remember, means que it's a source. Now let's compute the curve. The curve, we are using the dot product I, J, K. Partial derivative with respect to X, partial derivative with respect to Y, partial derivative with respect to Z, and here PQR, pero specific who is P, who is Q, who is R. E to the X sine Y, e to the X cosine Y, and Z. Okay, ready. I component, parentheses, delete this and this. Partial derivative C with respect to Y is 0. Partial derivative this expression with respect to C is 0. Minus J, this and this. Stay this and this and this and this. Partial derivative this expression with respect to X is also 0. And partial derivative over stay this and this and this and that. And partial derivative this expression with respect to Z is 0 also. Finally, plus K. Plus K, and you delete this and this. Stay alive this, 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 and this. Okay, entonces paréntesis. Partial derivative this with respect to X is e to the X cosine Y minus, and derivative this with respect to Y, derivative sine es cosine, positive cosine, no? Pero we have a minus, entonces e to the X sine Y. Sine Y, no, sorry, cosine Y, because derivative is sine with respect to cosine, with respect to Y es cosine. Entonces, let me repeat the idea again. The idea is clear. The derivative, this expression with respect to X is e to the X cosine Y, exactly the same here. Derivative this and this is partial derivative this expression with respect to Y, the e to the X is constant, and derivative sine is cosine. And this is 0. This is cancelled. This is 0. 0 vector. 0 vector. That means then that this vector field is conservative. If it is conservative, this is a moment to find the potential function. At least the first time that we are doing this. Find the potential function. Let me show you how. In this moment, we determine that this vector field is conservative. Therefore, this vector field is gradient vector field. Then exists, when this situation happens, exists one potential function. And thus the relationship, this component is df dx. This component is df dy. And this component is df dc. Y our goal is find f, que es the potential function. Ok, entonces df dx is equal e to the x sine y. If I want to find f x comma y comma z, I suppose we have three variables. You integration this antiderivative with respect to so you antiderivative fx dx. With the antiderivative of this, you consider that sine y is constant, and antiderivative e to the x is e to the x sine y. It's a coincidence that it's the same, but your specification here arbitrary constant, but actually it's no arbitrary constant because we are solving differential equation, but a partial differential equation because it's partial derivative. So it's not c, it's arbitrary function that depending on y and c, que este another variable, que do not participate in the integration. To understand this is easy. If you differentiate this with respect to x, so partial derivative e to the x is e to the x, you consider that sine y is a constant, and when you differentiate this part, do not depend on x is 0. It's similar to the calculus 1, but now you include no arbitrary c constant. No. You include one arbitrary function que depending of y and c, que es the variable que do not participate in the integration. Likewise, we are doing three times this process. The f dy is equal e to the x cosine. You apply the antiderivative again. We compute the same function. I suppose que es the same, no? I suppose que es the same. Antiderivative fy dy. You integration this with respect to y. Entonces e to the x is a constant. Antiderivative cosine is sine. Okay, wow, it's the same, look. Plus arbitrary function I call h that dependent of x and z, get the two verbs that do not participate in the integration process. Finally, the f dz is equal c, is our last component, and the antiderivative is so f x comma y comma z is the antiderivative of f and c dc, que the antiderivative z, que es 1/2 c squared, right? Because depending only the c, plus another arbitrary function q, let me call q, that depending x and y. Okay, this is super easy to integrate this idea in only one function. So our fantastic potential function is the function que depends of the three variables, que es the connection, union. Okay, union without repetition. You take this expression is repeated here. I take only one time, and you take that, and this complemented the equal part. So my potential function is e to the x sine y plus 1/2 c squared. This is my potential function. Not necessary to do, but let's check in Bauer. Not necessary. You compute always like that. Suppose I want to find partial derivative of the potential function with respect to x. You differentiate this function with respect to x. The answer is e to the x sine y. Suppose you differentiate with respect to y. This expression is e to the x is a constant, and derivative sine cosine. Differentiate with respect to c. This is a constant, 0, and use the power rule is 2c to the only c. It's exactly the same, the original component that we have at the beginning in our vector field. Potential function, vector field, conservative, gradient vector field, and this is the procedure to find potential function. Always it's the same. Okay, to finish that video, I want to discuss two important ideas. Suppose the vector field like that. It's totally radial. It's totally radial because it's a gradient vector field. Okay? This nabla F is capital F. So you compute the curve of this vector field. Es obvio que es zero because it's irrotational. We have no rotation, never. So you put together this expression to say the curve of the any gradient is always zero. Okay, makes sense. Now, suppose a vector field is totally, completely different rotation. Okay, but this rotation, but we have no source. Entonces, the curve of course exists, it's not zero, it's different to zero. But the divergence of the curve is zero because we have no source. Okay, so this is important relationship between gradient and curve and divergence and curve. Okay.